Okay, we represent the system we were just looking at by two ramps. I've arbitrarily got them the same length. That's not necessary, but the ramps did have the same length, so we can throw that length in. In any case, the length of this ramp is L, the length of this ramp is L. If we want to have two different lengths, we could subscript L1 and L2. Slope of the first ramp is going to be S1. Slope of the second ramp is going to be S2. Now, when we say the slope, we're not doing this relative to a coordinate system. We're just doing it relative to the horizontal direction. So the slope is just the magnitude of the slope you would get on a coordinate system. We have the first ball at some release position. There's the interface where the two ramps meet, and then we have some final position. So if we release the ball from some position here, it will end up at some final position here, and we want to be able to analyze that. Now, let me reiterate what we've already seen, or at least what I've already asserted is very easy to prove. But for a small slope, the component of the gravity parallel to the incline, the component of the gravitational force parallel to the incline is equal to the weight times the slope. That's a little vague. I should put the word gravitational force in there. I guess I'd better. And I'm going to be cluttering things up here, and that might be difficult to read even with the decent resolution of the video. Okay, anyhow, the gravitational force component parallel to the incline is the weight times the slope. And we're just talking about the magnitude of the gravitational force, since we don't have any vectors, any arrows up here. Okay, and that's the weight times the slope. And that implies that the free acceleration is equal to the slope times g, where g is the acceleration of gravity. So that knowing slope S1 and S2, we know the magnitude of the acceleration on both of these ramps. Now, this is an approximation for small slope. So let's make sure we know that that's a small slope approximation. It doesn't apply to larger slopes where the sine function essentially differs from its linear approximation at its initial point. So free acceleration is equal to the slope times g. By free acceleration, I mean the By free acceleration, I mean the acceleration in the absence of any forces other than the gravitational component. So when we have when I say free acceleration with the quotes around free, I'm referring to acceleration that results from just the gravitational component, and the condition being that the gravitational component parallel to the ramp is equal to the net force, or the net force is equal to that gravitational component. Under those circumstances, that's what I mean by free acceleration, and under that circumstance, this is going to be your acceleration. And I'll probably ask you to prove that. Not particularly difficult, but you want to be sure you understand why it's so. Okay, so let's put some symbols in this. Let's say the release position is x sub 1, 1 for a position on the first ramp, and then with a 0 here to indicate the original position, that t equals 0, the starting position on an interval. So it's at point distance x1, 0 above the interface. Above is in quotes. Above really means higher than, and that's going to be important soon, but what I really mean by that is this. So this is going to be x1, 0 from here to here. And then we want to find the final position, which will again be presumably measured from the interface. That's a convenient point from which to measure both of these positions. Okay? So what we want to do, and what we're going to do, is we want to analyze the motion of the ball from release to rest. Here's its acceleration, here's its initial position, and of course it's released from rest. So you should think through how to do that. You should pause the video and think that through. but I'm going to interrupt the video here, but it'll continue in what will seem to you like just a few seconds. Okay, to analyze the motion from release to rest, I can set this up. What do we know about the motion in the first ramp? That the change in position is going to be x1, 0. The acceleration is going to be slope times g, which is s1 times g. And the initial velocity is going to be 0. So in the first ramp, delta x1 equals x1 naught, a1 equals s1 times g, and v01 equals 0. And I've been a little inconsistent with my subscripts. I should call that v1 0. Okay. So we're going to find v1f and delta t1, the final velocity on ramp 1 and the time interval on ramp 1. Then we analyze the second ramp. We can't analyze the motion on both ramps with just one set of equations or one line of analysis, because the acceleration is different on the second ramp than on the first. And the acceleration is not a continuous function, so it can't easily be integrated. The result being that basically we don't have a uniform acceleration or a smooth acceleration. We have a discrete change in the acceleration, and that kind of limits what we can do if we don't proceed to just separate the motion on the two ramps. Okay, the second ramp, we have what? The initial velocity in the second ramp is the same as the final velocity in the first. We reach the end of the first ramp at the same instant we start the second ramp. Now, in reality, we have a little bump here, and we have to deal with that, but we're ignoring that for the moment. The acceleration on the second ramp, I'm going to say, is negative s2 times g. Implicitly, in setting the initial velocity in the first ramp equal to the final initial velocity in the second ramp equal to the final velocity on the first, I've assumed that the positive direction is in the direction of motion of the ball as it goes down this ramp and then again as it goes up this ramp. In that case, the acceleration in the second ramp is clearly in the direction opposite the motion of the ball when it's on that ramp, so it's negative s2 times g, and the velocity of the final velocity of the ball on the second ramp is going to be 0. So we see that on both ramps we have 3 bits of information that allow us to analyze the motion, either by direct reasoning from the equation, from the definitions, or by the use of equations. And of course, I haven't said it, so I don't know why I said of course. In this situation, it's going to turn out that we really need to use the equations of motion, or either that or go back to the first principles and integrate our acceleration function to get the velocity function to get the position function, which we could certainly do. We have a constant acceleration, easy to integrate. We can put our initial velocity into the integral to get the velocity function, and then we can integrate that, and we have the condition on our position function. However, we're going to probably just end up using the equations of uniformly accelerated motion to analyze this, and I suggest that you proceed to do that, or at least to outline it and see that you are able to proceed through that analysis, which is, once we have the 3 conditions on each motion, not particularly daunting. I'm going to, again, I recommend you pause, and I'll be back and again, what seems to you like a couple of seconds. Okay, the 2 equations of motion that we could choose from to make progress on either of these situations are these. And the first and second equations of motion are going to contain at least 2 unknowns each, and you're not going to be able to use them directly. And you're not going to be able to reason this out directly. We'll see why a little later. But It's mainly because there's no direct connection between acceleration and position. The connections between acceleration and velocity, and you just, sort of like acceleration and position information is too far apart to be reasoned out directly. Anyway, in any case, this equation, for the information we're given on the first ramp, we know the final velocity, the delta, the time interval. We know the displacement, the acceleration, and the initial velocity. So we know the acceleration, the displacement delta x, and the initial velocity v naught. So that we can directly find VF. All we got to do is plug in the quantities and we get VF. And I've done that here. So V1F, the velocity, final velocity of the ball on the first ramp, is just plus or minus the square root of V1 naught squared, the V naught squared, and the 2A delta x, A being S1G and delta x being your X1 naught, the displacement between the release point and the point where the ramps come together. So that's very straightforward, and it's also going to be very straightforward since we've implicitly chosen a positive direction to the right as this figure is drawn, that we're going to have a final velocity that's positive and not negative. Now I want you to pause. Well, okay, let's talk about this. I'm sorry. We could also use this equation. We know the displacement, we know the initial velocity and the acceleration, so we could solve for delta t. And there's no reason not to do that except that you have to be careful. This equation is quadratic in delta t. You're going to have to use the quadratic formula, or if you want, completing the square. And you're going to have a plus or minus on the discriminant, the square root of the discriminant, and you're going to have to make a decision about plus and minus. And it's going to be a little more confusing than solving this because it's very clear that we use the plus in this case. And having this information, we're going to easily be able to find the time interval from the existing information. Now, if I haven't said so already, you should pause the video, don't look at what I've written here, and think how you're going to analyze the motion for the second ramp. Okay, hopefully you've done that. I've got a flow diagram, what I call a flow diagram here that we looked at recently. We know V naught, VF, and A on the second ramp. From that, we know average velocity in the second ramp, just average V naught and VF, and we know delta V, just subtract V naught from VF. If we put delta V together with A, what do we get? Think it through, pause for a second, make sure you understand, and we get delta T. And you need to be sure you understand why that's so. Having found delta T, we combine that with V average, and we get our displacement, delta x. So using that, you got your V1F, you've got all your quantities here. You should be able to come up with an expression. See if you can do that, an expression for the final position on ramp 2.